Hey kids, this is Mr. Cozy, and this is video 48, talking about exponential functions. We will look at the form of an exponential function. We will compare them to linear, quadratic, and cubic functions. We'll break down and look at the anatomy of a graph, and then talk about how to get anchor points out of an exponential function. One of the things that we will do tomorrow is graphing these and graphing transformations. So it's important that we are able to pull out anchor points. Okay, so let's get started. An exponential function is any function of the form. Oops, let's go back here. An exponential function is any function of the form f of x equals b to the x, where the b is what we call the base of the exponential function. The base has to be positive, and it cannot be 1, because if it's 1, it's super boring. Okay, so an example of an exponential function is something like f of x equals 2 to the x. So I take any x value and make it the exponent of 2. Okay? So as x increases 1 at a time, this is going to double in size. So let's take a second and just compare exponentials with the other types of functions that we have talked about recently. I'm going to shrink this down a little bit. So let's start out looking at the graphs of 3 functions that we know something about already: 5x, x to the second, and x to the third. And then let's adjust the window so that we focus on the positive side of just on the first quadrant. And we will go 20 by 20. 2. Okay? There's the line. There's the second graph. Here's the third graph. Now, if I expand this out a little farther, let's go up to 40, and let's take my x's down to 2/10 so that I can see the graph a little better. Oops, I think I only got 1 there. Yep. Y max is 40. X max is 10. There we go. Sorry about that. Okay, here we go. So there's the line, there's the quadratic, there's the cubic. We see that starting out, the line is larger than either the quadratic or the cubic. But as x gets larger, the other two graphs catch up pretty quickly. X to the third catches up first, which makes sense. It catches up by the time x is 2. This is almost larger than 5x. X squared catches up a little bit later, but in each case, these two functions quickly catch up with the line, and it makes sense because these other two functions have a higher degree. Okay, and if I put in something with an even higher degree, like x to the 5th, we would expect that to shoot up pretty quickly. And even more so if it were to the 10th. Okay? There it is. So, with all of these polynomial graphs, the larger the degree, the faster it grows. Okay, and x to the 10th grows really, really fast. The thing about all of these, though, is that all of these functions and any other polynomials I could list get crushed by any exponential I can put here. 2 to the x starts out pretty slow, but as I zoom out and go bigger on the y-axis, let's go up to 100. There's the line, there's the quadratic, there's the cubic, there's the 10th degree. 2 to the x surpasses the quadratic. If you look at how quickly it is growing, it is on course to surpass the cubic, and it will even surpass this giant 10th degree function eventually. Any exponential function, it just gets huge in comparison to the other, to any polynomial that we list. Exponential functions and exponential growth is the most powerful force on the planet, second only to love. So that's how these humble functions compare to the polynomials that we have been looking at all year. They utterly crush them. Utterly crush them. So let's take a second and kind of take a look at the anatomy of this function. So I'm going to graph 2 to the x again, all by itself. 2 to the x. I'm going to fiddle with the window a little bit. X is negative 10 to 10. Y is going to be negative 5 to 15. And we'll go a mark every one and a mark every one. Mark every one. Okay. So there's the graph of 2 to the x. What you don't see, and let me grab a picture of this. What you can't see here is, let me grab that. Where's my lasso? There it is. Blow it up. Is the graph actually starts, it goes like this. Okay? On one side of every exponential graph is a horizontal asymptote, a line beyond which the graph can never cross. Okay, and as a default, the horizontal asymptote starts off at the x-axis. Okay, this means that while every exponential has a domain of all reals, its range starts out just above 0 and goes up to infinity. Okay, so every exponential has a horizontal asymptote on one side, and then it shoots up on the other side. Okay? If the base is larger than 1, it looks like this. If the base is smaller than 1, it goes the other way. It goes like this. And we'll talk about why in a little bit. Because we are graphing exponentials tomorrow, let's talk about how to get anchor points. Okay? The parent function is always the base, whatever it is. Let's try 3 to the x raised to the x power. And the base will change depending on the function. So in this previous example, the base is 2. Over here, it's 3. Just that all alone without any other doodads is the parent function. Okay, so and I'm saying that, guys, because tomorrow we'll look at how to graph something like this. Okay, where there's a lot of other transformations happening to the function, and we need to look at this and say there's the parent function. Okay, so there's my parent function. My anchor points work exactly the same. X is always -1, 0, and 1. Y is always what you get when you plug these x's into the parent function. Just the parent function. Okay? So if x is 1, 3 to the first is 3. If x is 0, 3 to the 0th is always 1. And if x is -1, 3 to the negative first, remember a negative exponent tells you to flip the fraction, so this is 1/3. Okay, so these are the anchor points for 3 to the x. If I wanted anchor points excuse me, for 2 to the x, I would use the same 3x values and plug them into here. So when x is 1, y is 2. When x is 0, y is 1. And when x is -1, y is 1/2. Okay? We'll use this anchor point stuff tomorrow when we graph exponentials. But I think I've given you enough to think about today, and I'm probably over time. Oh, holy crap, I am. Okay, I'm going to wrap this up here. Have a great day. I'll see you later. Bye.